The claim that was made in this warm-up question today was that U5 and U10 are isomorphic, U10 and U12 are not isomorphic. So some small group, first of all, tell me maybe first about the second statement, that U10 and U12 are not isomorphic. Did you come up with a good reason for why that is the case? Yeah.
In the reading, it said that...
So one of the things about isomorphism, so isomorphism, by the way, it's the first time we're saying this word in the course this semester. Every other time before today, what synonym have I been trying to use? The same, yeah, exactly. So now we finally have a mathematical principle that will put the same onto a concrete footing. Isomorphism means two groups are the same, and their elements are somehow the same as one another. And so if it's true that U10 and U12 were the same, they would have to have all the same properties as one another. But your argument is that one of these groups is cyclic, the other group is not. By the way, how do we know that U10 is cyclic? What are the elements of U10, by the way? 1, 3, 7, and 9. And what is a generator? 3. So it turns out that this is a cyclic group with 4 elements in it. You can check that 3 generates this group. I think we actually physically checked this once upon a time. What about U12? What are the elements of U12? 1, 5, 7, and 11. And why is it not cyclic? All of the elements are involutions. Well, all of the non-identity elements are involutions. Yes, exactly. So another way to understand what's happening here is to look at the orders of these elements. The orders of the elements 5, 7, and 11 in U12 are... You can check that 5 times 5, 25, that's equal to 1. 7 times 7 is 49, which is equal to 1. 11 times 11 is 121, which is equal to 1. So all those non-identity elements have order 2. Meanwhile, what's the order of 3 in U10? Order is 4. It's a generator, after all. It has to generate all of the rest of the elements. What about the order of 7? 7 has order 4, and 9 has order 2. So just looking at the orders of elements, we can tell that there's a difference between these two groups, right? This group has an element of order 4, a couple of them. This group has no elements of order 4. So these two groups cannot, in fact, be isomorphic. So one of the main reasons why we want to be able to tell when two groups are the same is we want to be able to tell when two groups are different, right? We want to be able to spot the differences that actually matter and be able to be blind to differences that don't matter, which I want to talk about in just a moment. One of the theorems that we'll see is that two isomorphic groups for any given order will have the same number of elements of that given order in both groups. So it's not enough to just have 2s and 4s. We have to have the same number of 2s and 4s among the orders of the elements in the groups.
Do they have to be in the same order? So like would it be 4, 4, 6?
No, because after all, that's getting to one of my next points. One of the things that we don't want to care about is we don't want to care about, let's talk about U5 for a second. How do we know that U5 is isomorphic to U10? Well, the question said so. I mean, yeah, that's what do they call that? A leading question in the courtroom. So, all right. So, by the way, don't take my word on literally anything. What are the elements of U5? 1, 2, 3, and 4. Okay. Is it a cyclic group? What is an example of a generator for U5? 2. Let's check it, right? 2 to the power 1 is going to give me 2. Remember, the operation is multiplication, so these powers really are the powers that you're thinking of. 2 to the power 3, that's 8, which is congruent to 3 mod 5. Right? And then 2 to the power 4, 16, that's congruent to 1 mod 5. So sure enough, the powers of 2 account for all 4 elements in this group. So this is a cyclic group that has 4 elements. So then why is it the same as U10? Why is it isomorphic? Say again? So let's draw what I call a hunters and arrows diagram for these two groups, which is a kind of diagram that you probably drew a lot in Math 180 when you studied functions. So U5 over here, U10 over here. Here are the 4 elements of U5, 1, 2, 3, 4. Here are the 4 elements of U10. 1, 3, 7, and 9. What is an isomorphism? So when we talked about groups being the same several weeks ago, one of the ways that we answered that question is we wanted to look for elements that have the same properties in both groups, right? And one of the important properties that the same elements would have to have are what are their orders, right? So if we want to know how to associate to one of these groups, elements of the other group that have the same properties, one of the ways to do that is by taking, for example, an element of order 1. By the way, what's an element of order 1? The identity. And what, therefore, should I associate that element to in the other group? Right. If we're associating elements with identical properties to one another, the identity we will always want to be associated to the identity in the other group. So 1 is the identity in both of these groups. So we should probably associate those together. Now, what's the order of, what did we say the order of 3 was in U10? 4. So this had order 4. Give me an example of an element of order 4 in U5. 2, the generator, right? One of the generators. And so one of the things that we could do is we could associate those with one another, right? They have the same order, so they're a good candidate to be associated by this function that I'm setting up here. All right. So now here's a question. If I associate 2, whatever I associate 2 in this group with on the right side, what happens if I take 2 times 2 in this group? Where do I end up? I end up at 4, right? So 2 times 2 is going to give me 4. Let me just, this is like super groundbreaking mathematics for today, right? 2 times 2 is 4. So, yeah, just put a little circle around 2. 2 times 2 is 4, and so that ends up there. So if I'm trying to create an association, a function here, of elements that have the same properties on the left side as they do on the right, what should I associate 4 with?
3 times 3.
3 times 3, exactly. Whatever I associate 2 times 2 with in the group on the left, I better associate the image of 2 times the image of 2 to that element on the right. And what's 3 times 3? Yeah, groundbreaking again, right?
Why can't you just do it because 4 to the whatever 4 squared is gonna give you the order of 2 and 9 has the order of 2, so they both have 4.
That is another good reason why we need to associate 4 with 9. Absolutely. So we could have said one of the other clues. Now, I'm being a little dicey, I'm being a little cagey about this for a reason. Because order, having the same order is a necessary condition for being associated by an isomorphism. It is not a sufficient condition. So what it can do is it can tell us when 2 elements should not be associated with one another. They should not be associated if they have different orders. Right? I shouldn't associate this 2 with this 9, for example, because they have different orders. So we know those can't be connected by an isomorphism. But just merely having the same order as one another is not necessarily sufficient cause to be associated by an isomorphism. So I'm trying to get us to a place where we're seeing something a little bit deeper, I guess, which is to say that the reason we wanted to associate 9 with 4 is that 4 was 2 times 2 and 9 was 3 times 3, and 2 is associated with 3. Right? So there's only one thing left. What does 3 go to?
1.
3's got to go to 7. Yeah, right. Super groundbreaking mathematics, right? There's the pigeonhole principle. One spot left. It's got to be that one. And so what I've done here is I've constructed a function. Function named phi. Right? So this is a function for which phi of 1 is equal to 1, phi of 2 is equal to 3, phi of 3 is equal to 7, and phi of 4 is equal to 9. Now, tell me what properties this function has. The hunters and arrows diagram makes the one really important property obvious. It's a one-to-one function. It is also an onto function. And therefore, what's the fancy word that we give to it? It's a bijection. Sometimes called a one-to-one correspondence, but I like bijection better. It's a bijection. So what also does that guarantee about the domain and the range, about these 2 groups? If I have a bijection between 2 finite sets, what do I know for sure about those sets? So because by nature an isomorphism is a bijection of the set of elements, we know that when those sets are finite, when our groups are finite, in other words, that means that the groups will have to have the same number of elements, i.e. the same order. So not only do the elements have to have the same order when they're connected by an isomorphism, the groups that are connected by an isomorphism have to have the same order. Which wasn't diagnostic for U5, U10, and U12, because all of those groups have order 4. And so finding a difference in the orders of those groups wasn't enough to tell which one was not isomorphic to the others. But looking at the orders of elements, or looking at the cyclic property, for example, of U10 versus U12, which is really kind of the same thing as looking at the orders in a way, that was a way to find a difference. So the reason we want to talk about isomorphisms is that if we don't know what groups are the same, then we won't know how to spot the differences that matter. And the differences that don't matter are things like, well, the names of the elements, right? So in U5, the names of my elements are 1, 2, 3, and 4. In U10, the names of my elements are 1, 3, 7, and 9. Right? So on the surface, those look different. But the structure in those groups is the same. Everything's the same, only the names have changed. Right? 1, 2, 3, and 4 have just been renamed 1, 3, 7, and 9. But all of the algebra that characterizes those groups is identical in one situation as it is in the other, when two groups are joined by an isomorphism. So it's not enough just to have a bijection of elements. We also have to have this other property. And this other property was sometimes called the product rule. This probably would have been part of the reading. So an isomorphism has to have two characterizing properties. The first is that it must be a bijection. Phi from G to H is an isomorphism if, first of all, phi is a one-to-one correspondence, a bijection. But what's the second requirement? How do we guarantee that not only does it have the same number of elements, but that the elements are behaving in the same ways?
Preserving the operation.
Yeah, it has to respect the operation. What does that mean?
It's preserved.
Yes? What does that mean?
So,
The operation stays the same between one and the other groups.
Yes, right. Any operation, so here's one way to say it. Any operation that I could do to the elements of this group on the left, right? Any operation I could do in G, I could get the same result by doing the operation in G and then crossing over with the isomorphism. I would get the same result as if I first crossed over with the isomorphism and then I did the operation in H instead. Right? So the operation in the groups commute with phi. Is another way to say that. If I do operation first and then I cross over with the isomorphism phi, versus if I cross over first and then I do the operation in the range, that those two answers need to be the same answer. So isomorphisms respect not only the elements, but also the structure, the operation in each of those groups. And the product rule is the formula, the equation that describes what that actually means more concretely. So let me get that back into this diagram. So phi of G times H, where that times is the operation in G, is phi of G times phi of H, where that operation times is the operation of H. So I suppose I should have decorated this here. G with the operation dot, and H with the operation circle. Because that emphasis is important when those operations are different, which they may be. Here we go. So there's the product rule. So an isomorphism has to do both of those things. Right? Get you a function that can do both. Be a bijection, a one-to-one correspondence, and also satisfy that product rule. That's how it gives us the same elements that have the same properties.